Today we are going to do the investigation of compounding interest, exponential growth, and geometric sequence. So we're gonna see how these kind of relate, and you'll find out, yeah, they do relate in some ways. So let's go ahead and start. Complete a table like the following for $1,000 invested with the compound interest at a rate of 5% per annum, compounding annually for 10 years. So you could do that here. I'm actually gonna do that on Desmos, and I will share my screen when I do it. Sure, why not? Okay. Oh, didn't work. Apparently, did it not work? Didn't register. Okay, that's fine. Just do it here. Mm, 360 degrees. Matter. Okay, anyways, so year one, year two, year three, year four, year five, year seven, year eight. Uh, all right. So year one, we're starting with $1,000. Year two, they already filled it in for us. 1050. Now year three, we're gonna multiply it again. So so times 50. So we're gonna go ahead and get 1102.5, and we're gonna get 157.625. So notice that every year we are slowly earning a little tiny bit more. Not a big amount, but it's gonna become noticeable soon. All right, times 1.05. Also notice that we're also growing in decimal places. Pretty cool. So right now we could pretty much see that instead of growing by around $50 per year, we're actually growing by a lot more. Growing by around 60 now. So this is where compound interest has a significant benefit over simple interest. And there we go. That's it. This is the entirety of it. So at the end of the 10th year, we have earned 1,000. We have earned $551. So we gain at least we gain half of our money. And let's go ahead and plot this graph. So before we go ahead and plot it, actually, I want you to refresh your memory a little bit, and let's make an equation out of this. So if we wanted to make an equation out of this, what would this be? This would be some sort of, an exponential function, right? So let's do a what? Whoa, what is this? Oh, a at t. Actually, oh, it's the text box here. My fault. So let's do a of t. A is equal to our principal being 1,000. Our interest rate is 1.1 plus 0.05 to the 10th power. And let's see if let's see if these do match. So let's go ahead and switch to decimals right now. So if of x is equal to 1000, 1.05 to the power of x. So f of 10, sorry, f of 9, because we had a year 1. If we did year 10, it would have been the 11th year, actually. So f of 9. And let's go ahead and plot all of this on the graph. So 1, 1000. So what we're trying to do here is that we're trying to make sure that, hey, look, we have made a correct function that represents this beauty right here. And note that there's actually more decimal places. Is that my calculator and potentially your calculator is ignoring these decimal places because there's way too many. Okay. All right. So let's see. Does ours match this graph? And no. So now let's think about it. Why does ours not match the graph? So this is where it comes to an interesting part, where we're actually talking about the ninth year here, but we're talking about the 10th year on the bottom. So if we erase this and call this one 1, you'll find out that all of our points are magically on the graph now. So what is the restriction here? The restriction here means that at day 0, we must have 1000. And now, if we have day 0 at 1000, day 10 would give us this new number. And this is the only part. This isn't the only part where mathematical discrepancy occurs. When you get on into calculating finance for dates, you'll realize sometimes you're missing a day because you're talking about days. So day 1 is actually a day. It's inclusive. So you have to add that. Anyways, let's go back to our work. So what kind of sequence do we see? We are seeing a geometric sequence. So a geometric sequence. What is the value of A? There is A. The initial value is 1000. C. What is the value of R? Is 0.5, 1.0. Or you could say the common difference is this. Yeah. Use the values for, okay, so we already did. T. Alright, let's go ahead and get into this. So we already substituted this. And we graphed the value as well. So we found out that it's a little different. And our compound interest, when we use the formula, it's right here. This is our formula. So we also graphed this, right? So we realized that there was discrepancy between what's actually being graphed and our graph because we had our table because we had a year 1. So now considering my shape of these graphs, so I could clearly tell that I have an exponential function. So it gets steeper and steeper over time. And it's always increasing. So there is a y-intercept most definitely at our starting point, which is 1000. there the y-intercept represent the initial investment. So at time t, before any time has passed, our investment is currently worth $1,000. Each point of the curve represent a point in time where x is the number of years passed after our investment and y is how much our investment is currently worth. So function which a variable is an exponent is called an exponential function. The graph of an exponential function models exponential growth. Explain whether the formulas representing investments are exponential functions. So yes, they indeed are because we do have an exponent here. Oh, why is my pen not working? So yeah, we have an exponent here. So we indeed do have an exponential growth. But note that at our start, we had 8 of t equal to 1,000 times 1.05 to the power of t. Whenever you have a variable inside, well, on an exponent, as an exponent, then you know for sure you have an exponential function. So why is it reasonable to join the points? We already answered this for simple interest, but we can basically our investment is growing. No, not only on a timely basis, it's growing every single second. So even though the interest is not applied, it's still growing every single second. Suppose I have invested 1,000 earning compound interest at a rate of 6.0. Predict the appearance of the graph. So the appearance of the graph is going to be generally similar. However, I'm going to be even more steeper because I'm compounding for a bigger amount. Now this is the last part, and it's pretty interesting because it actually talks about real life applications. So two kinds of Canadian savings bond and regular Canadian savings bond and compound Canadian savings bond. Regular Canadian savings bond earn a simple interest. Each year the interest is deposited straight to the owner's bank account or mailed to the owner. Compound instead earn a compound interest, so the interest is reinvested or the whole amount of the bond is paid when it's cashed. Copy and complete the table for simple interest, for regular simple interest. So you can do this. I will do this, I guess, as well. Wow, why is my text box always upside down? Okay, that was perfect. So I also do this with you, even though I think it's unnecessary. Actually, no, I will do it on decimals. Alright, so let's go ahead and start a new function. So at year 1, or actually no, at year 0, I'm going to do this. At year 0, we're going to have 500. Year 2, year 1, we're going to have 560. 2, we're going to have 620. 3, 680. 740. 800. 4, 5, 6. So at this point, this is where you would usually, stop, right? Wait, no, how much percent? Sorry, it's at okay. It's at. I was like, wait a minute. I thought it was at 12%. So yeah, our growth is a lot less. I was expecting something like this. So we're growing by $30 each year. I also write this. So we're growing by $30 each year. It's simple interest. So the sequence right now we have is just an arithmetic sequence. We're adding by 60 each year. So we also have a formula to find simple interest, though I don't think you really need it, but they do tell you about it. So A equals principal plus principal times the interest rate and the amount of time that's passed. So A is equal to principal, which is 500 plus 500 times our interest rate is 6%, so 0.06, and we have 8 years. Let's go ahead and calculate that. So we're gonna earn $740. And if you looked at our decimals graph, indeed that is what it is. At the 8th year, we're gonna earn $740. Now let's write the equation of this. It's pretty simple. It's pretty simple. This formula basically gave us the equation. So we know that our intercept is going to be at 500 because that's how much we started. Now it's all about how you're going to define your variable. So I will go ahead and multiply these terms together. So 500 times 0.06, and that's going to give me 30. Alright, because we're growing by 30 each year. Okay, I'll do t. 30t plus, and our intercept 500, and we're done. So let's go ahead and check on decimals to see if that actually matches with what we have. And you look at it, yes, indeed it does. We have all the points fitting on the graph. And that is it for our investigation of compound interest relationship with exponential growth. Oh wait, no, there's more. I'm sorry. Anyways, complete the table for, oh, I knew it. Okay, so we're gonna do this compound interest instead. So we're gonna hop on Desmosol again, and it's just interesting to see the comparison of of um of this. So let me remove this. So it's interesting to see the comparison of actually exponential growth versus. Can I put it here? All right. Yes, this is awesome. So side to side by side. Awesome. So year one, 500 times 1.06, 530. The first year is always going to be the same. And now this is where we differ. We earned a slightly 1.8 bucks, which is a good thing. It's going to be more next year. So we earned 5 more bucks. Good. And now this is where difference actually kicks in. We earned almost 10 more, which is very good. We earned even more. That is $20. So you see, this compound interest is pretty powerful. We're earning by almost extra. So we're extra by so much. Look at this. We have been we're almost making $800 at the end of eighth year, which is pretty good. We have earned around 660 more dollars. So the sequence in the table right here is geometric, and we can develop a formula for it. So and okay, actually no, let's use the compound interest formula, because why not? We are doing compound interest. So if you don't remember, it was A equals P of 1 plus I to the power of t. So it would be P. I guess I'll just write 500. It will be 500 of 1.06 to the power of t. And when we have this 500 to the 1.06 to the power of t, so now we can input whatever we want. So let's go ahead and do. Let's just do 8 to the 8th. So out of the 8 year. So let's go ahead and calculate that. 1.06 to the power of 8 multiplied by 500. You're gonna go ahead and get 796 point da 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 da. So it's gonna be the same thing as we got on the decimals. Pretty good. So now this graph compares the amount of bonds in the above tables. Decide which graph represents linear or exponential growth. So clearly compound represents exponential growth because we're growing a little more every single year. And you know that regular is linear. So if compound starts bending away from a linear graph, you know it's most definitely not linear. So that means we can actually relate two things. We can relate. Wow, why is this? We can relate two things. So number one, we can relate that compound interest plus geometric sequence plus exponential growth. That is the first thing that we have. And our second thing is arithmetic sequence. Simple interest plus arithmetic sequence plus linear growth. So we can see we can group them. These are the two groups. So describe why someone might choose regular. So if you want paying every single month, definitely choose regular because you're getting a set amount every month. But if you really want to make good money, you want to make extra money, so you could definitely want to buy compound instead. If I was investing 100,000, I would choose compound because compounding with such a big principal, I'm gonna earn a lot more. And actually, instead of just yapping about it, I'm gonna graph it on you. Graph it on decimals. So assuming we're using the same interest rate. So year one. So Actually, no, I'm gonna do year zero. Year zero, we have 100,000. Now, 100,000 times 1.06, that's gonna give us straight up 6,000. Good. And next year, look at how much we're earning more. So regular, this would have gave us this would have gave us this is how much I would have got. But instead I got this much. And now if I multiply it again, I'll get even more. Right? Which is such a huge principle. My compounding interest, it's so much more effective than simple interest. So for me, I would definitely invest it into compound. That's it for today.